Hello everyone, my name is Ivelin Georgiev and I'm a PhD student at Stockholm University. Today I'm going to talk about one of the projects that I've been working on, which is simulating the end of cosmic reionization. A brief table of contents. I'm going to introduce what the Apocorianization is and then talk about different simulations and modeling techniques. Then I will discuss about different types of statistics that we can perform on this simulated data, primarily neutral islands and their sizes, and studies of the 21 centimeter bias. And outside of 21 centimeter cosmology, I'll also discuss the ultraviolet background of ionizing photons and the Lyman alpha optical depths from quasar spectra. So what is the Apocorianization? It's a phase transition that occurs within the first billion years of the existence of the universe. And in terms of this talk, it's related to the 21 centimeter signal emitted from the intergalactic medium. During the cosmic dark ages, the neutral hydrogen within the intergalactic medium can emit 21 centimeter depending on how it's coupled to the CMB in its environment. But the growth of the first ionizing sources, so galaxies and stars, will create large ionized bubbles which do not emit 21 centimeter radiation, which will slowly mask away the signal until the universe is completely reionized and the 21 centimeter signal from the IGM disappears. What makes this very cool and interesting that this is a phase transition that starts on small scales, guided by astrophysical processes, and encompasses cosmological scales, and it contains information about both. Now, the key parameter that I study within this work is related to the mean free path of ionizing photons when we model the Apocorianization. It's particularly difficult, as I've said in the header, but let me introduce it to you. So what is the mean free path parameter? Well, it's the average distance an ionizing photon will travel in the ionized medium before it approaches an opacity of 1, so an absorption fraction of e to the minus tau. And on the right, I've given you a sort of example, little figure that we can use as a toy model. We can imagine that this is a large ionized bubble in yellow, and the outside is neutral hydrogen, and there's a luminous source at the center. So an ionizing photon can travel from the center up to the very edge of the bubble and become absorbed by neutral hydrogen clouds, as we say sometimes, or actually during its travel within the ionized regions, it can become absorbed due to either residual neutral hydrogen, which has either been kept by self-shielding systems that have not been ionized, they're self-shielded, or residual neutral hydrogen that has come about from the recombinations within the ionized regions. So the first effect is usually quite well modeled, even on large-scale simulations, such as the one that I will introduce to you. But this effect B is particularly difficult because it requires a very high resolution. And quite often, we sort of want a mix of both. We want very large simulations of around 500 H inverse co-moving megaparsec, and we want many of them to match our future observations, but we also want a very fine grid in order to resolve these. And that can prove to be quite difficult. So in fact, what we do is we introduce this effect B into our simulations, and this has been done in the field in many different ways. So in the context of the simulations that I've been using, the C2 ray simulations with a slightly smaller box, I introduce 3 of many models as a sort of a highlight for you to understand, and I've given them catchy names with the hope that you will get them. So for example, the first case, seen in yellow, and all of those models that I'll show will be in yellow hues, have a hard barrier. So you can see the dotted line on our little picture to the right. You can imagine that the ionizing photon travels up to a certain distance, in this case 20 co-moving megaparsec, and then simply it is stopped. If it has managed to travel this distance, we just assume that it must simply encounter some sort of absorption or Lyman-limit system and to have been disappeared. Another way is number 2, which is the soft, where you can imagine like we almost like put a mist in the entire simulation. It's such that once a certain distance has been traversed by the ionizing photon, additional opacity has been accumulated such that the optical depth is equal to a tau of 2 at a given value. And we use this Vorchek fit from 2014 based on quasar spectra. It's worth pointing out that this value is 2 just because of our simulations. Another case is to actually have no cutoff for Lyman-limit systems and to simply boost the clumping parameter within our radiative transfer. If you take the radiative transfer equations and you solve them in equilibrium, you can sort of boost the recombination rate by a certain scale. And within the field, usually a number of 2 or 3 is found to be appropriate. So this is why this has been chosen. So you can imagine within the yellow region, now the recombination rate becomes twice, is scaled by a factor of 2. So more ionized regions, maybe particularly towards the center, will have a higher fraction of residual neutral hydrogen, which will then impede the growth of bubbles. So onward to the first statistics, where I studied the neutral hydrogen islands. I put this picture for aesthetic purposes, but you can sort of imagine here are the neutral islands. They connect and they have very interesting shapes. And this is the residual neutral hydrogen, so the ionized region, similar to our picture. And this statistic that I will show, I trace different rays across these, let's say, these bubbles, even though they have a more complex shape, to try to get some sort of average value of their sizes. This method has been called the mean free path bubble size distribution. It's usually done for ionized bubbles, but I use it to do the neutral islands instead because I want to understand their sizes. And this is for our 3 models, hard, soft, and clumpy. As I've said, the colors sort of matched at a fixed neutral fraction. So globally, the neutral, it's within the last 20% of the universe is neutral, so the end of reionization. We can see that the hard and the soft model, they don't look that different, even though they use very different approaches. And you can imagine the clumpy model, you would expect that the bubbles would, without having any cutoff, would these neutral islands would be much smaller. But in fact, I think that the boosting of the recombination rate does cause an effect. So in reality, there's less smaller features, but there are some larger ones. So the neutral islands within the clumpy model reside in some of the furthest away cosmic voids away from any ionizing sources. However, if we go down to a point where only 8% of the universe is roughly ionized, so you see the redshifts are different. We can discuss this more in the panel, but only 8% of the universe is left. The bubbles have sort of evaporated. Maybe I can go back. You can see this. It has gone down, while the yellow one kind of stays the same. So for the clumpy models, the neutral hydrogen bubbles are evaporating. So more and more sources are appearing. They're more unbiased as we go down in redshift and more, which helps sort of evaporate these bubbles. While the hard and the soft barrier sort of impose a boundary. So even if there are sources closer by, they cannot interact if they are not up to that distance. This sort of relates to the Obler's paradox. However, I can also take the whole field, the whole simulation, and study the 21 centimeter power spectrum. This is sort of work that I have done in the previous paper, and the paper is highlighted here, while this is work that I'm now finishing. But what you can sort of understand is I take a cross correlation between the 21 centimeter field that you saw before and the density field, and I relate them to get a bias parameter. What's really nice is that this sort of relates to different cross-correlation studies, and this bias is a very interesting probe of the state of the IGM. And you can see, even though it might be difficult maybe for you to understand with few context, is that even though that now we've looked at the first case, only 20% of the universe is ionized, we see the amplitude of the bias compared to different K scales, which are inverse megaparsec, which relates to the length scale. Even though the neutral islands seem quite similar, the power spectrum analysis of the same data tells us very different things. So compared to the previous work, I have seen the hard model has a sort of cutoff based on the ones that we've imposed. So the 21 centimeter signal we would get, which is the potential probe we could measure with future telescopes, such as LOFAR, MWA, HERA, SKA, among many others. This feature has been imprinted on the spectrum, while it changes for the soft barrier, and it's completely different for the clumpy model. So even though the bubbles, the neutral islands, seem relatively the same, the power spectra look quite different. And this happens even later on. when the universe is now only 8% ionized, the feature for the hard model remains fixed because the bubbles cannot grow any more than 20 comoving megaparsec. The soft model, it is growing but much slower, and the clumping model remains pushed. What's interesting about this bias, for example, you can think, since this is a cosmology conference, is that the hard barrier sort of tells us that anything above this scale is a sort of relatively biased tracer of the density field, while past this scale it's more related to the astrophysics. But of course, this has been applied for simulation purposes as well. So it would be difficult to get this information out because also, for example, if we make a different type of implementation, the behavior changes. But we can see that even though initially it didn't seem like there's much of an effect, in fact there is. And this will be corroborated by the next thing. I've sort of decided to name it residual neutral hydrogen because all of the parameters I discuss after are affected by the residual neutral hydrogen within my cells during the end of reionization. But you will see these parameters right now. So I'm going to talk about the UVB, the ultraviolet background of ionizing photons. This is a measurement that usually comes from quasar spectra. And you can see some measurements exist at a redshift of 6 and a redshift of 5. And usually the common conception was that the universe ionized at redshift 6. Now with more data coming in, sort of suggesting that that might be close to 5.3. So that kind of motivates us even more to accurately model how the UVB, the ultraviolet background of ionizing photons, evolves. And this is what I plot for these three simulations, the hard, soft, and the clumpy. And quite often, problem within the field that has previously existed that many simulations, in order to reionize the universe, actually end up overshooting this parameter. But we can see now that actually this is related to the mean free path. A larger mean free path is correlated to the UVB. It regulates it. And in this case, in the clumpy model, you have a double effect. There's no mean free path, so the UVB becomes boosted during the peak process of reionization around here, but also having cells that have a boosted recombination rate results in a higher ionization rate. It comes out of the equation causing a boost, which is, I guess, slightly inconsistent with the observation. On the other hand, the hard model exhibits a very different behavior. You can see that going down with redshift, the UVB becomes asymptotes because at some point no bubble can actually influence an area larger than 20 comoving megaparsec. So the sort of the UVB becomes frozen in terms of interaction scale because previously it's been facilitated by the fact that if you have a cell, the more sources that can perceive it, they interact with that cell, they ionize it, and the ionization rate there is higher. So this is not very consistent. Well, the soft model seems to behave quite nicely. It's initially lower and boosts high up. And this is more consistent with hydrodynamic simulations such as CODA, CODA 3, CODA 2, Thiessen, amongst many others that sort of show this. Those simulations have slightly smaller boxes, but have a much, much finer resolution. So we can count on them to tell us this, and we can learn from them. Something else that I do is I take this data, the residual neutral hydrogen, and play a lot with it. I create a different code and analyze and sort of recreate the cumulative distribution function that can be that comes from calculation of quasar spectra. And for example, here's some data from Bosman 2018. They're newer ones, but that's just what I've put for the moment. And quite often you can see that I've not put these redshifts because they do not match my own, but this is sort of redshift 5 to redshift 6.2. And these figures, among many others, show this interesting behavior that sort of indicates to us that the universe at that point must be in the process of reionizing because the cumulative distribution function is changing. It's evolving from this more step function feature to this more skewed feature, which tells us that the mean of the distribution of the effective optical depth is changing, and also it's becoming skewed. What I should also mention that the effective optical depth is calculated from the flux of the quasar spectra. So I try to play around and recreate this. And again, I'm showing you my models. at a fixed neutral fraction for the different cases. And you can see that the hard model struggles to reproduce this. It doesn't actually have these lower values of tau effective, because also by limiting the interaction between the different ionizing bubbles, the ionization rate is lower, so the residual neutral fraction within the cells of the ionized medium is higher. So actually that flux is slightly larger and the tau becomes bigger here. And usually it cannot, even if we see further on, it cannot reproduce this feature, so it's not as skewed. Well, you can see that the other two models behave a bit better. And here we can see at the lower redshift. What I should point out is maybe when the universe is completely reionized, there will be much less of a spread because there would be no residual neutral islands, and perhaps there would be a more homogeneous UVB background, so this would be more like a step function. And you can see here that again the soft and the clumpy models behave a little bit better than the hard model. So in the previous work, we sort of saw that the hard model, this hard break, impacts the shape of the 21 centimeter signal. We saw this in the bias, but now we can also say that the imprint continues further in the ultraviolet background in other tests, while the soft and the clumpy model behave a bit better. And I've done many other models that are quite interesting, and I'd be very eager to talk to you about them, but right now I don't have the time. So I want to leave you with my concluding remarks. The last stages of reionization are difficult to model, but contain a wealth of information about neutral hydrogen in the IGM. This information is imprinted on the 21 centimeter bias, and the MFP implementation regulates the UVB background of ionizing photons. And we can also observe this effect in the Lyman alpha transition. So thank you for listening. It's been a pleasure. I look forward to chatting with you, and feel free to reach me at any time. I will stop this share. Have a nice day.